Hello, welcome back to the playMath tutorial channel. In this lesson, we will be looking at limits of a rational function with a radical sign. So we will be rationalizing. So let's do that.
Took a swing at a wrecking ball and I prayed for my downfall.
But before I get into that, I want to show you guys three things. So the first thing I want to show you is the identity function. Let me do this in red. So the identity function is this. The limit of x as x approaches a is equal to a. And this is because the thing I showed you in the last set of videos or in the intro video. Remember the function x. It is a straight line that cuts through the origin and continuing. So what the identity function is saying, any point here, remember when I was telling you that this is symmetric, so if this is 1, then this would also be 1. So the limit at any point will be the same value as here. So if this was 2, well, 2 would be here. If here was 2, going up would also be 2, and 0.5, as I showed you in an example, would be 0.5. So this is what the identity function is saying. Constant function. So the constant function is as this. The limit of a constant, k, as f of x approach any point a is equal to k. And that is because this. Look at this function of a constant. Say I have a constant 1. My 1 is here. So I have a horizontal line that goes through 1. Any point I choose on my x-axis, any single point, if I choose here, that's 1. If I choose here, my function is still at 1. This should be perfectly horizontal. I know it looks a little bit slant, but it should be perfectly horizontal. So any point I choose, my function will still approach 1. So if this is a, or this is a, or this is a, any single point, 1 will be the limit. And I hope that is clear. And next thing I want to show you guys, I watched the video, I posted the first video already, and I was watching and I realized that my explanation for the 1 over x curve wasn't as clear. When I'm going through limits at infinity, I will explain to you guys this function a little better. But for now, say this is a, right here is a. As x approaches a from the left or from the right, the limit of this function approaches this point here, right? Unlike if when I'm at infinity, I will do a better example, as I said. But for now, if x is, say, for example, 1, if I substitute 1 inside this, my limit would approach 1, right? So the limit of 1 over x as x approaches 1 would be 1 over 1, right? So this is where I'm coming from, meaning this is what I use to explain this. If I'm coming from the right or from the left, then my limit should approach the same point, even though this curve is slightly going down. Infinity would be a little different, and I said I will do that in infinity, so let's leave that for infinity. So back to rationalizing, or limit of a rational function with radical sign. So that's the topic for today. Let's get into that. Now say you are given this function. Let me use this marker. You are given this function, x minus 5 over root x plus 4 minus 3. And your question is to find the limit of that function as x approaches 5. So right away we see that this is 0 over 0, which is indeterminate. If I directly substitute my 5 for x, then this would be 5 minus 5 over 5 plus 4 under the root, which would be 9, and the square root of 9 would be 3 minus 3. So that would be 0 over 0. In cases like this where you have a root in your denominator or even in your numerator, at times you will have to rationalize. So let's show you how to rationalize this function. Now in this case it's the denominator that we have to rationalize, because we can see that there's nothing we can do to manipulate the numerator in this case. And there's a root here, so that's a good way to see that you need to rationalize if you have an indeterminate form when you substitute values. So this is how you rationalize. You write back your function as is. Then you multiply the function by the conjugate over the conjugate of the denominator. And what is the conjugate of the denominator? The conjugate is just simply switching this sign, the minus sign, to a plus sign. Or if it was a plus, you would switch that plus sign to a minus sign. And you don't change this sign under the root. Why you don't change that sign? You're looking at this as two terms, because you're looking at the root as one term and the 3 as a next term. So the only sign you will change is this minus 3. So, or the minus in front of the 3. So you will change the minus to plus. So this is what you would have. Root x plus 4 plus 3 over root x plus 4 plus 3. Now I multiply these out. Straight away I see that this, I can write this as, let me do the denominator first. So I can write this back as x plus 4 squared, because there are 2x plus 4, minus 3 squared. If I multiply these two, because I want to show what I did, if I multiply these two out, I will get this. I don't have much space to show everything, but I hope that you understand. If you don't, please leave a comment. Now this would be x minus 5 times root x plus 4 plus 3. And I'm all out of space. So let's go back up to the top. So I'm going to erase and rewrite. So now this is what I have. So let's simplify. Remember when we did, let me fix this plus sign. When we did surds, if you watch the surds video, I said that if you have the square root of a raised to the square, or let me say m root. If you have the m root, which is any root at all, of a raised to the m, or m root of a with m outside, then this would be the same thing as just writing a, because this cancels the root. Same thing goes for the square root. For a square root, you don't have to write a 2 here, because it's known generally that there's a 2. So the 2 cancel the square root. So I'm left now with whatever is under the square root. So I rewrite this back now as x minus 5 times root x plus 4 plus 3 over x plus 4 minus 3 squared. And 3 squared is 9. Let me just write 9. If I subtract 9 from 4, I'd be left with minus 5. So let me do that. So I would have x minus 5 times root x plus 4 plus 3 all over x minus 5. And the x minus 5 would cancel, leaving me with, let me try and make space over there, leaving me with root x plus 4 let me put my root, plus 3. So this is what I'm left with now. Let me highlight this. So I will now find the limit. Remember our question was to find the limit. Let me write the question here. The limit of the question was x minus 5 over root x plus 4 minus 3. That was the question as x approach 5. Remember, this was our question. So now we simplified our function, and we rationalize to simplify our function to this. So now we can directly substitute. So if I substitute my 5 for x, I'd have 5 plus 4 under the square root, which would be 9 plus 3. So 9 plus 3, root 9 plus 3, and root 9 is 3. So the limit of this function as x approaches 5 would be 6. And that is how you rationalize the denominator. So let me now do a next example, then I will rationalize the numerator. So here's a question. The limit of x minus 1 over root x plus 2 as x approaches 1. If I directly substitute 1, I would have 0 over 3. And 0 over 3 is not undefined, but I'd get a 0. For my next question, I have the square root of 9 plus x squared minus 3 all over x. And I'm finding the limit of this as x approaches 0. So if I substitute 0 in my equation, I'd have the square root of 9 minus 3, which would be 0 over 0. And this is indeterminate. So this time, I said that we were going to do a next example with the radical sign in the denominator, but I'm running out of time, so I'm working with the radical sign in the numerator just to show you guys how we do this. So the same thing goes, you multiply by the conjugate, except you're multiplying by the conjugate of the numerator. So I will rewrite my function, minus 3 over x. And I multiply this by 9, root 9 plus x squared. And I multiply this by root 9 plus x squared plus 3 over the same thing, root 9 plus x squared plus 3. And this is the same thing as multiplying by 1. So I'm not actually changing anything. In the numerator, I have root 9 plus x squared all squared minus 3 squared over x times root 9 plus x squared plus 3. That is what's in my denominator. Now these square cancel and this will become 9. So I have this. Let me erase. Remember that this was squared. So this squared would cancel the square. So I'm left with 9 plus x squared minus 3x over x times root 9 plus x squared plus 3. And this is multiplying this. Now this will be x squared on top, because 9 minus 9, 3 squared is 9, so 9 minus 9, I'm left with x squared on top over x times root 9 plus x squared plus 3. This is basically x times x over x. So there's a 1 here. and this 1 from indices will subtract from that 2. So I will be left with x in the numerator over 9 plus x squared plus 3. Now we can directly substitute. Remember, the question was the limit of root 9 plus x squared minus 3 over x as x approaches 0. So as x approaches 0, this function approaches 0 as well. But let's evaluate this. So now we directly substitute 0 into this. So straight away the numerator will be 0 and this will be 0. So I have 3 because the square root of 9 would be 3 plus 3, which would be 0 over 6. And 0 over 6 is not undefined. Neither is it indeterminate. It's actually 0. If you put this in a calculator, you will get 0.